I think people have been giving them either 10 or 12. Make sure they don't go over
Make sure they don't go over
12.
8 and then 3 days. I like to have like 2 days.
Yeah. Yeah. Yeah.
As long as I know, so I'm not giving mixed information.
Yeah.
Eight tasks to do.
I think I've been too not ambivalent, ambiguous about it. I said 10 to 12. And so I don't know what people have been preparing
Okay,
for.
but then that's fine because if they're done at 10, they're done at 10.
Yeah, but if they're not done at 12, then they need to be done.
I'll make sure.
Yeah, I mean, yeah, we haven't been off track.
You're missing a last name.
Is it like German or?
CHEXO?
Yeah.
No, in German, that's not how I pronounce it. That's how I ask.
As I saw in the office, and it's German, but like in German you would maybe say Loth or yes.
And just to say, so I'll return, I'm going to set like right here and I'll give you a 2-minute warning. Okay, so.
Oh, how do I?
Should be, yep.
All right. Hello?
Is this on? Okay, everyone, we're going to get started. Thank you. Okay.
Please. Attention, please.
So yeah, welcome to our final session of CHEXO. For those
Sorry
of you that
again.
don't know, I'm Emily Rickman, Easter astronomer here at STSCI. And for the first talk of this session, we have Corey Spohn, who's talking to us about how HWO's field of regard will impact scheduling observations of precursor science targets. Take it away.
All right. Can everyone hear me? Great. All right. So, my name is Corey Spohn. I'm a postdoc working with Chris Stark at NASA Goddard, and I'm here to talk about everyone's favorite piece of vaporware. So we're going to be looking at specifically how HWO's field of regard is going to impact our ability to actually use information we could get from precursor science targets. So I think we've had adequate motivation for this 25 Earths today. So I'm going to skip over and work on what do we want to use precursor science to do for HWO's objectives. So we have this quote from the decadal that says, for a direct imaging mission, we want to use precise radial velocities to identify terrestrial exoplanets. And the goal here is that we can either increase the yield of HWO or limit the risk by finding these targets ahead of time. And so now the question is, how well can we actually use this information? Like most yield modeling studies, it's kind of a, is this a problem? So what can we think about for this is just back of the napkin math. We're going to look at how many Earths are there for a future EPRV study to find. So if we take the preliminary HWO target list and say we have 150 stars and we set eta Earth approximately equal to 0.25, we get around 38 Earths are available for this survey to potentially find. Now, if we start eliminating some of those stars because they have too much stellar activity, you can't disentangle the Earth signal from the RV noise. What are we going to look at here? Now, this is a fun number because basically we don't actually know, but I'm going to take a very rough cut from talking to someone on the NUID team, and we got this 0.66 number based on stellar activity signals from the EXEP preliminary HWO target list. And this gives us a very nice 25 Earths. And so now the question is, how many of those could you actually find if you have different field of regard values? And what fraction of those can we image with HWO? And so now the equation looks something like this, where we have all of these different terms being multiplied, and we have this fraction that we can image with a different field of regard value. And the question is, what is the actual number of Earths that we can find? Now, I have this beautiful plot here that I generated to explain how I'm defining field of regard. And so we have this telescope sun line. We draw a 90-degree angle, and we define our field of regard based on these two pitch angles. So we have the maximum pitch towards the sun, and we have our maximum pitch away from the sun. And anything inside this cone of our field of regard we can see. And if you can imagine, as the telescope orbits the sun, these different target stars are going to come into and out of our field of regard. Now, if you are an astronomer, obviously you want these to be very large so you can get these targets at any time possible. If you're an engineer, you want this telescope to be thermally stable, so you want these to be more narrow so you don't have as much variation in where it's receiving its energy. And so how do you actually vary this and get a final yield value so we can estimate this fraction of the images? So I'm going to be using this tool called RV2 imaging that I've created. It's essentially a slightly higher fidelity yield model that tries to account for RV surveys and also like full scheduling of observations. So to do this, we create our planetary systems. And then we take those planetary systems and start running these through and generate RV survey data. And then with that RV survey data, so we essentially create RV curves for every one of those planetary systems that were available to us. We can run orbit fitting on all of the RV data. And then once we get the orbit fits out of this, we're going to calculate the probability of detection information, essentially what is the best time to observe this orbit fit with HWO at any given time for a given integration time as well. And then we can look at the actual scheduling problem, and I'm going to explain these two in full in a minute. And the point here is that once we have our imaging schedule based on our probability of detection information, we can then move forward, simulate the observations, and see how our yield changes and how sensitive it is to our two different pitch values. So we think about what is probability of detection for us in this case. So one of the big problems of going from RV data into direct imaging is the fact that RV is fundamentally incapable of separating our mass and inclination for the different orbits that we get. So we have all of these different orbits in the image plane are consistent with this exact radial velocity data. And so when you're trying to figure out what the best time to observe is, you probably want to be looking at a time when all of these different potential planets are visible. You also have effects of, as your telescope orbits the sun, you're going to be looking through different amounts of dust inside of our solar system. So we're going to have variations in time based on how much local ZODI you have to account for. And then we also have different errors on RV fitting. So obviously you don't get RV data that looks like this. And so when you run orbit fitting, you're going to have to think about how are you sampling from your parameter space such that you're adequately accounting for the errors in this. And so finally, what we look at as far as what the probability of detecting with HWO, something that has been detected with radial velocity, we're going to get a curve that looks like this. So on our x-axis, I have the time since the mission started. So you imagine HWO launches 2043, and then you move forward. In this case, I'm only plotting 2 years. And then you also have on the y-axis here, how long is your observation? So now I'm parameterizing. You have, say, you want to look at 1.5 years into the mission. You have to determine how long does my observation have to be in order to actually find all of the potential orbits that are consistent based on my radial velocity information. And now the question is, how do you actually use all of this information in a full simulation framework? Because this is a very messy set of data in order, if you want to find the best possible value for potentially 30 to 100 different planets. And the way we're going to be doing this is by treating it as a really disgusting traveling salesman problem. So we have a constraint programming satisfiability solver called CPSAT that is taken from the operations research tools package, which is maintained by Google. It's open source. And essentially, we discretize this set of probability of detection information, give each one of these different kind of discrete values. So say you cut out different 6-hour blocks in this mission and choose, say, 5 different integration times, just to limit the number of discrete Boolean values you have. And CPSAT is basically taking all of these different Boolean values that correspond to one block in this plot and it has a kind of, you have your true-false values that CP set keeps changing and determining whether or not one set of Boolean values represents a good schedule or not. And to map those on, so it's going to keep changing these. Now we need to determine what is actually a good schedule as far as we are concerned. You have to set some objective function. And in this case, my goal is going to be 3 well-spaced detections to understand the planet's orbit before moving on to spectral characterization. So this is essentially like the first step of a direct imaging mission where we're only looking to find the orbits well enough that it's worth investing potentially weeks of observation time in order to get spectral characterizations. And so what we're going to do is we're going to map those decision variables onto these integer variables b. So each planet gets a b variable. And what this equation effectively says is if a decision variable is true at a time when the probability of detection is greater than some threshold, add 1 to b. And this is cut between 0 and 3 so that it doesn't decide that the best course of action is to look at one target 100 times. And so finally, we have this objective function, which simplified, but essentially take all of these different planets' integer values, sum them up, and find the set of x values that maximize this sum here. And now this is what those schedules will look like. So I'm essentially taking, again, we have our time since the mission has started, and I'm squishing all of the probability of detection for a planet into one row. And then I'm mapping on these kind of like white boxes. You can see a couple. Some of them are just lines because the observations are so short. But essentially, those are when does the observation start and when does it end. And then on the opacity, you can see those define the windows set by our field of regard. So in this case, we have a very narrow field of regard. Both of our pitch angles are 5 degrees. And then over here, we have a wonderful 45-degree in both direction field of regard. And you can see now we have access to a lot more flexibility in our scheduling system. So just as a case study, you can see in this planet here, you never have a long enough observation time to actually use the information you got from RV in order to schedule an observation because you just don't have the 30 days you need to actually find this planet. You'll never reach the SNR required with these narrow windows. And over here on this, the 45-degree case, you do have enough time. So now we can actually look at what does it mean to simulate this in full, and I'll run through this kind of fast, but basically I'm using the ExEp HWO target list, ExoVista to generate my planetary systems. Extremely, extremely good RV data because that's not the focus of this. And then for my HWO parameters, I'm using the parameters used by Rhonda Morgan in her 2021 paper, which uses a 6-meter primary vector vortex coronagraph detecting at 500 nanometers. And I'm simulating my observations with ExoSims. And now we have our grid of all of those fractions parameterized by theta t, our pitch towards the sun, and our pitch away from the sun. And so we can start picking out specific values and see how much does this impact our ability to use the precursor science targets. So at the very widest field of regard, we're getting a 75% of them are useful for HWO. And that leaves us with 18. Now we have this kind of sweet spot you can see here where you don't have this significant drop, and we're getting about a 4% decrease from the maximum. And once you get down to the very lowest value down here, we're down to around 15 Earths from the potentially 25 are useful for us. And so that's if you only want one detection. In some cases, you might want to parameterize the orbit more carefully and take multiple observations. So if we look at what it takes to get 3 detections, now we have a bit of a more harsh cut in most of these cases. So at the widest field of regard, you're getting 16 of the Earths. Where we previously kind of had a sweet spot, you're down to 12 of the precursor science targets are useful for us for HWO. And then when you get to the very bottom, you're down to 10 of these Earth targets are useful for us for HWO. And I think I'm out of time, so I will put up my conclusions and take questions.
Do we have any questions? Hi,
Corey, great talk. This is Sarah Steiger from Space Telescope. I was just wondering how these, the field of regard also interacts, or if you have any idea of how it interacts with some of the other parameters that we talk about. Obviously, if you're, time to signal, time to SNR.
Yeah, that's something I'd love to run and open this kind of study up to more parameter values. So testing this with different coronagraph performance and different observation modes is something I want to run. I don't have a great feel for how they interact currently, though.
Any other questions? I would like to ask a quick question while Stephen comes up, and we can switch over if you want to. Are you planning, or have you put in any astrometric acceleration information into your orbit fits to further inform their?
I'd love to do that. I'd love to do that. So if anyone has any use or ways of doing that, please talk to me.
Okay.
But yeah, not yet.
Great, thanks. Well, let's thank Corey again.
Hello, can you hear me? Awesome. Okay, let me get up my, this one, no. Okay, where is my talk? It's this one. Sweet, okay.
Okay, so next up we have Stephen Schmidt from CHEXO speaking about resonant ultra short period planet systems, opposite ends of the exoplanet age distribution. Take it away.
Yeah. Ready? Hi everyone, I'm Stephen Schmidt, and today I'm going to be talking to you about how I have calibrated the relationship between age and velocity dispersion in the Kepler field, and how I have used this relation to infer absolute ages for two heavily studied subsets of the exoplanet population. So getting started, exoplanets are known to evolve. Yes, very surprising. And the timescales for this evolution to occur vary wildly depending on what process you're looking at. Some of these processes occur during the era of planet formation and can take millions of years, while others can occur on secular timescales and take billions of years. Now, if we want to get an idea of how long a particular process takes, we need to have precise ages for the systems for which the process is happening. And if we want to look at the very long-term billion-year timescales, we need to have precise ages for stars that are mature or similar in age or older than our sun. However, if we look at the methods that we have to infer ages for stars, including exoplanet host stars, we see that many of them, like the first three that I've listed here, are only applicable for young stars, and others are only applicable for evolved stars, so like not main sequence stars like the sun. And additionally, the method that we can use, isochrones, often ends up in uncertainties that are so large that it's hard for us to get any meaningful constraint on the evolution that's occurring. So we have to appeal to population-level analyses or ways of inferring ages, one of which is the galactic velocity dispersion. So how does this work? Well, the way it works is it involves how stars move around in our galaxy. So starting out, stars form in a very thin, close to the midplane disk in our galaxy, and over time they experience random kicks due to like molecular clouds or the galactic bar or whatever, and as a result, their velocities end up becoming more scattered and varied. And this causes them to move away from the midplane of the galaxy, and the net result is that if you take a population of stars and you look at the distribution of their velocities, which you can parameterize by its velocity dispersion, you end up seeing that velocity dispersion over time is a monotonically increasing function of age. And so you can see this in action with this calibrated age-velocity dispersion relation for the Kepler field. I made this by taking a sample of around 4,000 subgiant stars in the Kepler field that have ages that are precise to around 6%. I ordered the sample in age, and then I used a moving window of a subsample of this population and just calculated its velocity dispersion for this moving window to end up with this. And you can see that there is this nice line here with age on the x-axis and velocity dispersion on the y-axis, with this light gray shaded region representing the 1 sigma uncertainty in this age velocity dispersion relation. And so you might notice there is some structure here, and we can explain that with what happens to stars as they experience these random kicks. So initially, stars experience the kicks, and they move away from the midplane. They don't receive any more kicks because they're far away. They spend most of their time there. And so for a given population, its velocity dispersion becomes saturated. Now, this is true for a while. You get older and older. Until eventually you run into stars that are part of the so-called galactic thick disk that formed with a more varied velocities. And as a result, the velocity dispersion starts to increase once again. So that's a little bit of galactic archaeology for you. But going back to exoplanets, if you take the velocity dispersion that you calculate for an exoplanet population and you compare it to this age velocity dispersion relation, you can end up with a age range or a characteristic mean age for that exoplanet population. So what I'm going to do is I'm going to apply this method to 2 different subpopulations of exoplanets. I'm going to briefly talk about mean motion resonances. Well, eventually we'll then getting into the bulk of the rest of this talk, which will be ultra-short period planet systems. So getting into resonances. A mean motion resonance is a dynamical configuration of an exoplanet system where the period ratio between planets, like the x-axis on this histogram that I'm about to show you, is a ratio of like 2 integers. So like 1 to 2, 3 to 1, 4 to 3, something like that. If you were to make a histogram of the population of exoplanet systems, period ratios with like a multiple planet system, and you wanted to look at the resonances would occur here, where they have these labeled ratios of those periods. And so before the Kepler mission was launched, it was expected that a lot of exoplanet systems would be found in these low-order mean motion resonances, based on the idea that they experience convergent migration in their protoplanetary disk phase. However, this was the result. It was not at mean motion resonances, but instead, the peaks of this histogram of period ratios for Kepler-discovered exoplanets was instead wide of resonance. And so, as a result, a lot of theories had to be put together to explain this observation that differed from the original idea of this convergent migration. So, in addition to resonances, it has been found that resonant systems, or certain types of resonant systems, that is, second-order resonant systems and first-order resonant systems, where you have an innermost planet that is close to its star and affected by tidal dissipation, those types of systems are relatively younger than non-resonant systems, based on their velocity dispersion, which is, again, on the x-axis. And so the resonant systems, those types of resonant systems, have a colder or smaller velocity dispersion than the non-resonant systems. And so, yes, that's great. They're relatively younger, but they're not so much younger that they are any younger than 500 million years. And the reason we can tell this is because if we look at an indicator for age for these systems, like on the y-axis, equivalent, like lithium, equivalent width, we can see that the distribution of resonant versus non-resonant systems in these particular cases are indistinguishable. So the end result is that we find that these systems are young, but they're not so much younger than 500 million years old. We can figure out how young they are by looking at their velocity dispersion and comparing it to the age velocity dispersion relation. So by doing this, we compare them, and we find that these 2 types of systems, the tidally affected first-order resonant and second-order resonant systems, are younger than about 2 billion years old. This means that whatever process is causing them to leave resonance, which in the case for these tidally affected first-order resonant systems is like tides, and for second-order resonant systems is most likely not. The idea is that these systems, whatever is causing them to get out of resonance, occurs in less than 2 billion years. So now, moving on to ultra-short period planets, these are rocky planets under 2 Earth radii. Their periods are under 1 day. Famous examples include 55 Cancri E, Coro 7b, ones like that. They orbit so close to their stars that the expectation for where their protoplanetary disk ended is further away than where they are now. That means that these planets likely had to have migrated to get to where we see them today. Now, the details of this migration involve different timescales. Some of these timescales allow them to get there very quickly, like towards the end of the era of planet formation, to under 1 gigayear, whereas other explanations, like tides, allow them to get there over billions of years. So we can again appeal to the age-velocity dispersion relation to get an idea of how old these systems are, and we find that ultra-short period planets tend to have a velocity dispersion that's on the warmer side for exoplanet systems, which corresponds to an age range that's around a little bit less than 5 billion years to a little bit less than 6 billion years. And so this is great and fine and all, but if we want to figure out how they actually got there and how long it took for them to arrive, we want to look at the population of rocky planets with periods just outside the USP planet regime, i.e. planets that have the same radii distribution, like between up to 2 Earth radii, but with a period range of 1 to 2 days. If USP planets arrived a long time ago, these planets should have an age that is consistent with USP planets. However, if it took a long time for USP planets to arrive to where we see them today, these planets should be younger than USP planets. So, again, applying it to the age-velocity dispersion relation, we can see that they are in fact younger than USP planets, which means that USP planets have to be recent arrivals to where we see them today. And so this suggests that tidal dissipation might be one of the reasons why we see them here. So if we look at the coupled ordinary differential equations that describe tidal evolution under these differing tidal scenarios, we can make plots that describe the trajectories of these planets over time in terms of their orbital parameters, where we have on the left, we have their semi-major axis, in the center, their eccentricity, and on the right, the rotation period of the star based on a median rotating stellar, like solar model. And so we can see that if the stellar tidal quality factor is smaller than what models would expect for them, we can see that the planets arrive there. This is great and all, but it requires a smaller tidal quality factor. But if we allow the eccentricity to be excited to a small but non-zero amount, we can see that it also allows them to reach the observed location with a stellar tidal quality factor that agrees with what our models would suggest. So, in summary, we have this new system for determining absolute ages for exoplanet systems using their velocity dispersion. We find that the processes that diffuse mean motion resonance systems out of resonance occur between like 500 million years to 2 billion years. And third, USP planets are recent arrivals explained by in-planet tidal dissipation via eccentricity excitation and damping. And yeah.
Thank you. I finished with 5 seconds to spare. That was perfect. Questions? Oh, I'm looking too far out.
Hi, Jacob Bain, University of Chicago. Your eccentricity of 0.1, I feel like that would be pretty noticeable for those planets.
So going back to this, the eccentricity initially is 0.1, but the excited eccentricity is like 0.004 or something like that.
Okay.
Yeah, so it's like for rocky planets, we probably wouldn't be able to.
Well, so we're doing a lot of the secondary eclipse observations of rocky planets with JWST, and maybe it's not the same exact planets here. It's mostly around M dwarfs, so maybe it's a different sample. But we see all of those at phase 0.5, so the eccentricity seems really tiny.
Yeah.
So I'm not. Yeah, I don't know if that's consistent with this.
That would be the interesting thing to follow up on. I guess that since M dwarfs have a have a different stellar structure than the sun-like stars that we'd see with the Kepler field. That might lead to a different result, but that's definitely an interesting thing to do for these types of systems.
Any other questions?
Les Kempton, University of Maryland. When you're measuring the velocity dispersion of these populations, is there any evidence? Like, is it clear that it's all just one Gaussian with one velocity dispersion, or do you think there's subpopulations? Basically, is it characterized? Can you characterize the age by a single velocity dispersion?
So this is, I guess, a big point with using velocity dispersions. This is not a age for the entire system, but it's kind of like a typical age for the system. So I'm not saying that every exoplanet system with a USP planet is between like 5 and 6 billion years old. I'm saying that on average, like across the systems that we have observed, the typical age is an average age inferred via this method is in that range. So it's not, you can't use this to get individual ages for systems, but you can use it to get an idea of what the age range for the population is as a whole.
But you have no evidence that there's like two distinct populations within any of these groups of planets that you're looking at?
Not that I know of. I guess that part of the issue is that the samples that we use are like around like 60 planets already, and so it's like splitting the sample into smaller and smaller samples could result in like a lot of noise that would be like, you'd start running into issues of like p-hacking, I guess. Yeah.
Okay, let's thank Stephen again.
Yeah. Okay. I've got to find a kinds of keynote.
Okay, so next up, we've got Callan Lawson, who's going to talk to us about JWST chronography of debris disk systems, early results, and lessons learned. So when you're ready, take it away.
You guys hear me all right? Awesome. All right, so getting towards the end of the day here, but hopefully you guys will stay tuned for a little bit longer. So let's just jump right in. Does this laser pointer work? Cool, great. Okay, so debris disks. Hopefully you've heard about them before. I'm just going to briefly review. These are dust-dominated circumstellar disks that are sort of remaining after the epoch of planet formation. So these are thought to be continually replenished by collisions between planetesimals. And by observing these, by imaging them, resolving them, their morphology can reveal dynamical interactions, other interesting things, possibly including the presence of planets. And then on the other side, sort of multi-wavelength imaging can be used to constrain the dust composition and the dust grain size distributions for these objects. So in terms of imaging these at sort of optical infrared wavelengths, bright diffracted starlight from the parent star is the big challenge that makes this sort of difficult. And so the two kind of nominal ways we get around this, or at least I get around this, is coronography, where we just simply block out the central light from the star, and then reference star differential imaging, where we remove any residual light by simply observing a second star that doesn't have a disk, and then we can sort of subtract it. So why might we want to use JWST to observe debris disks? So some strengths first, right? It's very stable, very sensitive. The stability of the PSF over time makes this sort of PSF subtraction problem a lot more straightforward. And then also there's access to compelling wavelengths that are really hard to get from the ground, and certainly at this sensitivity. And so this gives us sort of favorable planet contrasts. It's a lot easier to find planets around these stars at these wavelengths. And then on the disk side, there's a lot of really cool disk spectral features there. So we can kind of use this to constrain, again, composition of these disks really well. So what's standing in the way of this? What are the challenges? So there's the usual disk imaging woes. If you're not familiar with disk imaging, these are things like oversubtraction, separating disk structure from artifacts, and specifically oversubtraction, because this will be relevant later. The issue is that we are taking, say, in the RDI case, We're taking a science target that has starlight and disk light, and we're fitting the starlight in that using just a simple image of starlight. So we end up sort of overestimating the brightness of the starlight and accidentally removing some of that disk signal. And the other more sort of JWST specific issue is the complicated PSF, point spread function. So in terms of shape, we have something like this here. If I can find the laser pointer. Yeah, so here's our PSF for near-cam coronography at 3.5 microns. Let's say we take a simple, nice circular disk model. We convolve it with the JWST PSF. We end up with this sort of weird hexagonal shape like this. And so that can obviously disrupt abilities to sort of interpret morphology. And then the other issue is that the PSF varies spatially. So depending on where you are on the detector, your PSF has a different shape. So this is kind of the worst case scenario, showing the MURI 4-quadrant phase mask, where on the right you're seeing the instrumental response at the position that's highlighted in green on the left. So it looks sort of like a kaleidoscope. And so the issue is that kind of the way that we go about solving these usual disk imaging woes involve being able to forward model, being able to simulate fairly accurately anyway, the instrumental response. And so the question is, do we have a good enough kind of understanding of this and this to be able to do that? And so I'm going to show you sort of from here out how we do this, how we get around these issues in the context of some results. Oops, I hit the wrong button. Perfect. Okay, skipping ahead. Okay, so first target is AUMIC. So we observed this as part of GTO1184, and this is a small M-dwarf planet imaging survey. So this is sort of a happy byproduct. We get the disk. So we observed this with NIRCam at 3.6 and 4.4 microns. And this is a well-studied sort of edge-on disk. So we expected to see the disk, and sure enough, we do. And this is novel in that this disk had not been detected at these wavelengths before, 3 to 5 micron range. And so what I'm showing here is on the right column, kind of the gold standard PSF subtraction technique clip. And you can see these blue regions. That's over subtraction, right? And so the entire photometry of the disk is affected. And if we want to be able to get accurate photometry, do meaningful sort of measurements for the disk, we need to figure out a way to correct this. And so this is kind of our favorite approach, which is model-constrained RDI on the left. And the idea with model-constrained RDI is that rather than sort of fitting the starlight in spite of the disk, we consider them both simultaneously. So we model the disk, we model the starlight at the same time, and subtract that starlight model. And so sure enough, it turns out that here's the MCRDI images here in the left column, the disk models, and the residuals. So indeed, we do, thanks to WebPSF and WebPSF extension, we can accurately model these extended sources and get some cool science out of this potentially. So moving on to target number 2, and so this was actually just published yesterday in APJ Letters, so go read it if you're into that sort of thing. So this is really cool. It's an M4 companion to Fomalhaut A, which is a very famous debris disk. This is a much older system, also a fainter star than AUMIC. And this disk was previously resolved in almost sub-millimeter by Cronin-Koltzman et al. 2021. But had scattered light non-detections for STIS and sphere. And so you really want to have both scattered light and thermal emission detections to be able to do meaningful sort of constraints on composition. So we observed this with NIRCam, again, same filters. And we end up getting the first scattered light detection from Fomalhaut C's debris disk. And so what I draw your attention to here, so we have the sort of disk detection on the left here. I'm highlighting some nuisance background sources. Turns out when you're looking this deep, space is lumpy and full of stuff. So on the right here, we just have the same image, but with the almost sub-millimeter contours. So you can sort of see it's the same general shape. And I'll just draw your attention to the sort of scale bar there, which is in micro-Janskys per square arc second. So this is a extremely faint disk. So who cares? Well, so this is one of only 5 M-dwarf debris disks that's been resolved in scattered light. And so M-dwarfs are roughly 80% of nearby stars, right? And we know next to nothing about them in terms of what debris disks can tell us. And not only is it one of only 5, but plotting it here in this sort of quick plot that I threw together of host luminosity versus system age, here's the other 4 M-dwarf debris disks that have been detected in scattered light. And here's Fomalhaut-C way over here. So it's just an entirely new class of object that we're seeing in scattered light. This really highlights a key strength, I think, of JWST for disk imaging, debris disk imaging, is that M-dwarfs, because they're so intrinsically red, in scattered light, they're actually quite relatively easy to detect with JWST. And so kind of circling back to talk about planet detection limits for both these two very briefly, we get very deep limits. Of course, we don't find any planets. You probably would have heard about that by now. I really would have buried the lead here if that were the case. But no planets, unfortunately, but we end up digging down to around a 10th of a Jupiter mass for AU-MIC, and around a Saturn, a little bit less than a Saturn mass for Fomalhaut-C. And this is really an unprecedented depth for these sorts of objects. So changing speed a little bit, Beta Pictoris. So we've just seen probably the faintest debris disk ever seen. Let's go to the brightest. So here's Beta Pictoris. If you've heard anything about debris disks ever, you've heard about Beta Pictoris. So this is highly inclined debris disk with multiple planets, one of which is we can see in these data, as you'll see. So we observed this as part of CHEXO11, which is led by Chris Stark. This is published in Rebolito et al. 2024. And so we have 8 filters, 6 in NIRCam and 2 in MIRI. And so you have the NIRCam filters here. So the NIRCam, we used model-constrained RDI that I mentioned earlier. For MIRI, is just simple classical RDI PSF subtraction. And so we've highlighted Beta Pic B there. You can just see it. And then maybe if you squint a little bit, you can see in the MIRI this sort of weird feature here. And so it turns out that we have enough signal-to-noise ratio and that we understand the JWST PSF well enough that we can do deconvolution. So we can sort of correct the blurring of the PSF, and we'll get a much nicer image of the sort of structure of the disk. And so this is nice because it lets us do comparable color measurements if we want to compare the brightness of the disk at different filters. But then it also brings out a lot of this structure here. And so again, this cool feature here. Before I move on to just dive into the disk stuff, I wanted to note that Jens Kammerer has a paper that should be coming out soon, not accepted just yet, but resubmitted any day now, is focusing on Beta Pic B in these data. So here's a zoom in of the Beta Pic disk with the cat's tail. And so you can see this sort of main disk plane here, what we call the extended secondary disk. And this has been seen in prior observations, but it's quite a bit more clear here. You have the cat's tail, and you have all of this stuff, right? And so you see this only in the MIRI. And the question is this stuff real? And so we actually have 2 rolls, 2 roll angles of the telescope, and we can orient these, so derotate them, to look at kind of separate the artifacts, detector artifacts, from the astrophysical signal. And so anything that's astrophysical should stay oriented the same way between these derotated rolls, and anything that's instrumental should rotate. And so what you can see is that a lot of this stuff in the background here is actually real. So there's a lot going on here, and this is, again, one of the best studied debris disks, and this kind of came out of nowhere. Suddenly we have all of this new interesting stuff, and so what are the explanations? So we have a few other pieces of evidence here. So this false color image, you can see the main plane here is quite red, and then all of this new stuff is quite blue. So this tells us that there's a distinct composition for this material, and that it's likely higher temperature. So then the other piece of evidence is, again, these features are not visible in scattered light. So what can we do with this? And so this is an effort led by Chris Stark, and I'm going to not do it justice in the minute that I have remaining. But basically the idea is that if you take a simple steady state collisional model, a pinch point model, you can reproduce a secondary disk and even a cat's tail if you have a certain composition, but you cannot explain easily the crook of the cat's tail, the color, or the brightness distribution along the cat's tail. However, if you add in sporadic dust production events, an ISM drag, and a secondary disk that contains organic refractory material, you can produce these sort of major observed qualities. So this is not the be-all end-all solution. There could be a different answer, but this is kind of the working hypothesis. And so we do have a MIRI MRS study that's led by Marshall Perrin that will hopefully answer some questions about these features. And so then just very quickly, sort of as a joke, I wanted to put these in context of each other. Here's all three disks at the same scale. If we multiply the two right ones by a factor of 20, you can see AU-MIC. And skipping a few orders of magnitude, there's some help C if we multiply it by a factor of 8,000. And so here's my summary and conclusions. And here is, just for fun, deconvolving JWST image of AB Auriga, specifically because Julian listed this as a target where the structure would be hard to observe with JWST, and I thought it'd be funny to deconvolve it. So it turns out that maybe we could. And thank you very much for your time, and I'm happy to answer any questions.
Thank you. Any questions?
Hi, nice talk. Tad Kamasic, UMD. So I'm not a debris disk person,
Sure.
but the one thing that everybody knows about Betapik's debris disk is that it's warped from scattered light. And I'm wondering if you can put together like the previous scattered light observations plus these near Cam and MIRI observations. Is the warp related to what you're seeing with the cat's tail and the secondary disk?
Yeah, so that secondary disk is the warp. So that is, it looks like a warp sort of in scattered light, I guess. But yeah, it's a sort of secondary inclined, very highly elliptical disk is what we think.
Got it, thank you.
Yep.
Any other questions? Otherwise, let's thank Helen again.
I don't remember where the clip part was. There you go.
Sure, that you are between us and beer. Okay, so last but not least, we have Matilda Marlin, who's going to speak to us about unveiling directly image systems with JWST MIRI. Take it away.
So hi everyone, my name is Mathilde. I'm a postdoc at the Space Telescope in Johns Hopkins University. And I will talk to you again with a direct image system with JWST observed with instrument MIRI. So this is a work that I've started last year during my PhD at Paris Observatory. So these are observation part of the EXO MIRI GTO, so from the European team. Just to highlight the population of planets that I'm looking at, so these are from the young giant planets, so the ones that we can resolve from the host star, so the direct image planets. And you can see on this plot that you all know of, representing the mass as a function of the semi-major axis, that this population represents a very unique place in this diagram. So these are very interesting planets, and most of them can be observed with spectroscopy, so we can have information on their atmosphere. But before JWST, we only had near-infrared data. But the mid-infrared window is very interesting, and we finally have access to this mid-infrared window thanks to the instrument MIRI. So first of all, we're going to get a favorable star-to-planet contrast for this planet, so it gives access to cooler and therefore older planets, also less massive planets. So this is the first thing that is quite interesting by observing the system at mid-infrared wavelengths. And on top of that, for the atmospheric characterization, it is quite interesting to get these wavelengths so that we can have a wider wavelength coverage, which is better to constrain the temperature and the radius of the planet. And if we can do some spectroscopy for this system, we can also access the chemistry of the atmosphere, better understand the vertical structure and many other things for all of these planets. I'm going to focus on a result from two programs from the ExoMIRI GTO, and in particular for the exosystem HI799, LG95086, and JG504. So we observed the 3D system with different sets of coronagraphs. So the MIRI coronagraphs are located on the left side of the field of view. So we have 4 coronagraphs. The first one on the top is the LEO coronagraph, so the one operating with the wide filter at 23 microns, and the other 3 are the 4-quadrant phase mask, which allow to get a better inner working angle, even though we are operating at mid-infrared wavelengths, and they are operating with very narrow filters at 10, 11, and 15 microns. They all have been designed in order to allow the ammonia detection looking at 10 and 11 microns, which we expect for the colder planets, but also to get better temperature measurement, looking at the slope of the spectra, and also for the characterization and having some image of disk, as you've seen on the talk just before. So they all show very good performance. Looking at the ERS image that you probably have seen already, and from the communicationing data, we have the contrast that were expected from 2 to 4, 10 to the minus 5, and we have a background limited observation at all separation above 1 arcsecond. So the first result that I'm going to show you, which is already published, so it's from the famous system HR8799 that you probably all know of because it's one of the most famous, as it has been observed 15 years ago. We have already many data. It has been observed with many instruments at near-infrared wavelengths. And so it is a young system that is often seen as a young solar system analog with 2 dust belts and 4 giant planets from 5 to 10 Jupiter masses in between these 2 dust belts. And these are our GWST observations with the 3 4-quadrant phase mask at 10, 11, and 50 microns. And the last one is a non-choreographic observation at 21 microns, so just imaging. So this is the observation that we get. So we also observe a reference star to be able to reconstruct this diffraction pattern that we observe and to subtract it using a method that we call RDI, so reference differential imaging. And this is what we get after that. So we have the observation of all the planets, so the B, C, D, and even the planet E, which is located at 0.3 arcsecond, which is good performance to show for this chronograph. So this is what we observe at 10 and 11 microns. And in a more unexpected manner, we also observe some bright emission in the middle at the 15 microns, which is also visible at 21 microns. And this is actually due to the emission of the inner disk of the system that is being visible. So the PSF of the star is more extended. So with the coronagraph, we don't perfectly hide the PSF of the star, and we also have this emission due to the inner disk. It was actually expected because the inner disk was known from the SCD studies from a couple of years ago. And by doing some modeling of this disk, we have been able to see that the radius and the flux of the disk was actually quite similar, even though a bit lower. And we also have a bright background object, slightly visible at 10 and 11 micron, but very visible at 50 micron, which we realized it was actually a background galaxy. So for each of these planets, we extracted the flux at each wavelength, and just for the planet B, looking at the atmospheric characterizations, so we put together the near-infrared data that we had and adding the mid-infrared information. So doing a simple chi-square analysis between 2 atmospheric grids models and the photometric data, we are showing that we can measure larger radius for the planet and also therefore cooler temperature by just adding these 3 photometric points, which is good because it is in better agreement with the evolutionary models. So we are not perfectly there yet to have the perfect fit between evolutionary model and atmospheric models, but it is already better than when we had only the near-infrared information. And we will have MIRI MRS data, so integral field spectroscopic data coming from this system, so we hope to be able to have a deeper atmospheric characterization for each planet and also for the inner disk. So looking at the second system that we observe within our GTO, it's AG95086. It is a little less known as HR8799, but it is quite similar system. It is further away, so it is fainter. It also has 2 dust belts, but with only 1 planet in between from 4 to 5 Jupiter masses. The planet is located at around 0.6 arcsecond. So this is the ALMA image put together with the sphere image of the planets. And these are the spectra from a study that came out a few months before having the GWST observation. So putting together all the low resolution spectra and the photometry to be able to infer the atmosphere of the planets. And they've ended up with 2 hypotheses. So the first one was that the planets have a circumplanetary disk with quite warm temperature from 14 to 16,000 Kelvin and a significant extinction. or a supersolar metallicity with lower temperature and small to medium amount of extinction. And as you can see on this picture, they show that the difference will be at a longer wavelength. So this is why we hope to have better understanding by looking at data with MIRI. So doing similar analysis as the system before, so we observe a reference star, we remove the diffraction pattern by doing some optimization to be able to remove it better, and this is the observation that we get at 10 and 11 micron, and also with the LEO chronograph at 23 micron. So it is with the wider chronograph, so all the part in the middle is hidden by the mask, and we have the detection of the outer disk, which is the emission that you can see. We have lots of background objects in these images that were not quite expected. So we have a background galaxy that is actually resolved, and also a background star. So all the G, S, and G2 are background star and galaxies that we've seen in the image. The planet is very faint and much fainter than expected, so it looks fainter than expected, but it is there. And once again, we have the emission of the inner disk that is very bright for this system. So extracting the photometry of the planet after being able to model the PSF of the planet, we extract the flux, and we run for one modeling using the atmospheric models ATMO and EXOREM once again. And by looking at the best fits, we have a few conclusions. So first of all, by adding the mean-infrared information, we reduce the uncertainties on the atmospheric parameters by at least a factor 2, but even much higher factors for some parameters or models, so mostly for the radius and the temperature. Once again, we've shown that the radius measurements agrees more with the evolutionary models measurements, and all of these results are more consistent with the second hypothesis that was made in the previous analysis. So we refute the hypothesis of having a warm CPD, otherwise the planet would have been brighter at this mean-infrared wavelengths, and it's more consistent with the supersolar metallicity and temperature between 800 to 1300 Kelvin. So looking at the inner disk component, we try to model it by using a simulation of chronographic images. So we've run some model with different radius and trying to best fit with the flux. So just to show once again, the inner disk of the system was inferred by the SED modeling as seen before. So by running this analysis, we've been able to model the inner component, and we've shown that the radius of the disk is mostly about 10 to 13 astronomical units, and the flux measurement is much lower, at least by a factor 2, from the spectroscopic measurement with the splitter data. So we are arguing that it is probably due to the contamination of all the background objects that we've seen in the images, because the angular resolution of Spitzer is much higher than the one that we have with GWST. So this SED modeling was probably a little off. By just having better angular resolution, we can compare all of that. After doing this analysis, we still have lots of residuals in the inner disk components, and this is still to be understood. So we cannot yet draw a perfect conclusion from it that's actually a physical signature or more of a signature due to the stellar subtraction. So still under investigation to better understand the inner disk or the shape of the inner disk that we are seeing on the chronographic images. And I'm going to conclude my talk by a last system. So this is JG504, which is a nearby system with a solar-like star. So it is a very interesting system. It has an age that is not very well constrained. Some very recent studies are saying it's 16 million years, but other studies are showing that with isochrons, the star is more about 4 gigayears, so a lot of different values coming from different stellar indicators. And it has a companion at 2.5 arcsecond, as you can see on this discovery paper, which is a T8 to T9 spectral type companion, about 500 Kelvin. And if you are looking at the age of the system, if you try to infer mass with evolution models, we have mass from 1 to 20 Jupiter masses, so it's not perfectly constrained. So these are our GWST images taken with the 3-4 quadrant phase mask at 10, 11, and 15 microns. And because it is a planet that is quite further away than the star, we didn't have any we didn't have any reference observation part of the program. So to be able to remove the stellar diffraction, we've been building a reference library using many different observations from the ERS, commissioning, and from GTO programs. And it actually shows that we can have the similar performance, but only for further away objects above 2 arcsecond. And if we increase the reference library, we can hope to actually have similar contrast, but also at shorter separation. And by extracting the photometry in the 3 images and running some simple forward modeling with the ExoREM atmospheric model, so we just had the 3 photometric points in the red with MIRI. We retrieve all the other near-infrared data points that we can have in the literature, and we show that we can confirm that this planet have some ammonia in its atmosphere, as it was expected from the planetary atmospheric models. And we can also have much better constraint on the radius of this object by just having the mid-infrared information, as seen for the other systems. And this is a very interesting target to me, and we will have observation with the MIRI MRS coming very soon. The opening window is in a few days, if I'm correct. So we will have spectroscopic data for the system, and we should be able to have much deeper atmospheric analysis for all of this system. And I'm going to leave you with my conclusion. So we have the first images of the exoplanet at mid-infrared wavelengths. So I've been showing 3 of them. We have the unexpected emission of the inner disk that is observed, many background objects in all of the images. And we are already trying to improve the atmospheric characterization, but with the, yeah, okay, just finish with that. And the spectroscopy will really help to better understand the full composition of the atmosphere of this object. Thank you.
Thanks for the great talk. Are there any questions, Elena?
Great talk, Mathilde. I was wondering for GJ405b, are you planning on getting any near-infrared data?
For the GG504?
Yeah, yeah.
Yeah, the NIRSpec data has been taken.
Oh, okay, okay. That would be interesting to see because you should actually have some gravity indicators which will also, you know, constrain the age of the system.
Sure. I think that'd be interesting to put together the NIRSpec data and the MIRI data. We will do that at some point. Marshall can talk about it because it's the PI of the NIRSpec data.
So cool, yeah. Congratulations.
Yeah, I can just answer that. Yeah, so we happened to get the NIRSpec part through one of my GTO programs. We got a little bit earlier. We've not yet gotten very far in the analysis of that, but we were working on that in particular with one of the grad students at UC San Diego, working with Quinn Konopaki and Nish Baburaj, who's going to be leading that, working with us and Keelan and with her. And yeah, definitely having the NIRSpec and MIRI together was always part of our grand plan, and I was able to arrange the GTO with the NIRSpec part, and then Mathilde and Polychronos led the GO to get the MIRI, and it's going to be fun.
That is actually one of the reasons why we didn't went further in the atmospheric analysis for the system yet with the chronographic images, because we're going to have the full spectra from the near to mid-infrared wavelength, so it's going to be very good to have the full atmospheric analysis.
Any other questions? I was just saying I'm very excited about it because it has a nice constrained dynamical mass, so learn a lot about the system. All right, last opportunity for any questions. I know it's the very end of the day. All right, otherwise let's thank Mathilde again. And I'm going to hand over to Josh.
Excuse me. All right, give me one sec. Got a few last words.
Yeah, in the meantime, I just want to say I've been posting pictures on the website. If you really don't want a certain picture, let me know, I can remove. And also, well, we never know, you know. Yeah, because yeah, it's too late, but I can, you know, I'm quick enough to do that. And also, if you want, if you have pictures you want to contribute, we can make an album or something, you know.
Awesome.
Including the happy hour.
Yeah. All right, a few last words. I just want to remind everybody of the Slack. Like I said this morning, it's going to be as useful as you want it to be. So if you want to put job postings, and we'll use it for the next meeting, maybe we can do monthly happy hours and stuff. Maybe we can make that an active thing. If not, it'll just be kind of the, I don't know, one of the many Slacks I have that kind of die. Want to remind you about CHEXO11, right? Hopefully, we'll have some venue that wants to host it. I'd be happy to travel, visit your institutions. So don't be afraid of organizing CHEXO12. Is this on? Is this on? I want to put up the test slide again. Is Allison here? Do you want to say anything about this?
Thank you. Hi, I'm Allison Youngblood, the test project scientist, and we have a call for community input on what science cases tests should prioritize in its extended mission. Submissions are due on June 14th, so not too long, but the submission process should be very simple. Just a casual 1 to 2 paragraph submission. We've also, if you go to our the Google form where you submit, we have a link to a guide where we've put together some information about the observatory and possibilities of changes you could propose, like cadence, pointings, stare duration, etc. And if you have any questions, we have a help desk, and we welcome any. Thank you.
Thank you, Allison. Got one more regional announcement. That's a save the date for a conference that just got accepted. This is something Guanwei is heading up, so I'll let him share the dates. If he doesn't.
All right, as we just heard from the last talk from Matilda, JWST has this unique revolutionary capability in infrared, so we plan to take advantage of that, and I'm happy to announce on behalf of the organizing committee, who's all in the room right now, please wave your hand. Yeah, that we're gonna have a conference on atmospheric characterization of exoplanets from rocky to giant planets, not limited to transiting, also including direct imaging planets in thermal emission. Just no reflected light, please. As long as you do thermal emission, exoplanet, we are happy to have you. And please save the day if that interests you. It's from March 30th to April 4th, 2025. And the official website and application will be announced sometime this summer. And one thing to notice that this conference format, maybe if some of you guys have been, it is has a lot of free time in Aspen. There's a large, long midday break, usually from like 11 to 4, that allows for. No, I'm not making this up. If you go to the website, this is a historical tradition for interaction on and off the slope, wherever you want, and it's kind of. Yeah, we study hot stuff at the cold place. And the size would be roughly like this, 100 people, so more greater for focused discussion and the sheer new results. Okay, thanks.
Yeah, so looking forward to that. Thanks, Ryan. All right, a couple more things. As we wrap up, I want to give some special thanks, some shout outs to some people that made this meeting possible, including the new Space Telescope Director, Jennifer Lotz, and Linda Smith, who heads up the Director's Discretionary Research Fund, which is what provided you all with breakfast, coffee, and lunch today. So we thank them for their coverage there. And food that was provided by Karma's Cafe here at the Institute. Karma Halterman was very helpful with that. There's also Sharita Hana, who helped with the events and planning group to give us all the materials and name tags and stuff. Steven Schmidt, who's been helping out with photography. Let's think of that. Thomas Marufu and Gary Gilbert in the AV box, who have been helping us with streaming it and getting all the projectors to work, so thank you for that. I want to thank Nestor Espinoza, Munaza Alam, Nikolai Nikolov, Emily Rickman, Marga Caruthers, and Keelan Hoke for helping us with the session chairs and welcome table, so thank you for that. And I want to give a shout out to Space Telescope Facilities and custodial staff who's helping us clean everything, make sure everything's set up for you to come here, so shout out to them. As well as the points of contact in the SOC who helped do the abstract selection and helped us with all the submissions. So thank you to everyone. And thank you to you all for coming. It was a lot of fun to see everybody. Thanks for driving up to Baltimore, braving the rush hour traffic. Please drive safe on your way home. But it was really great to have you. And hopefully we can do this again in 6 months. If you want to keep the good times rolling and you want to avoid rush hour for the next, I don't know, hour or so, we're going to have a happy hour at Nepenthe Brewery. So I'll show you a map in a little bit. There's the address if you want to Google map it. They got drinks, beer, cocktails, non-alcoholic food. They got a good vegan menu. They open at 5, so we kind of need to loiter a little bit. So take your time getting there. This is the Google map there. We are here at the Institute. You can walk through the forest there and get there a little bit quicker.
If it's not raining, I can take a group and walk there. If you're happy to walk, I'm gonna walk.
It's like 1.5 miles at most.
It's like 25 minutes, yeah.
Yeah. That'll help buy some time as you get there. But it's pretty close. Nepenthe Brewing Company. And I think that's it. So thanks again for coming, and hopefully see you again soon.
Yeah. And also, like, send your feedback and suggestions on Slack, maybe. Thank you, Josh, for doing most of the heavy lifting, I would say. And I'm going to keep talking through.
Thanks for coming. You're going to come to Nepenthe? I'll see you soon. Yeah, I'm excited. So what's next? Do you like send me a manuscript? You're on that too?